the exponential function is usually defined in the real numbers, and always takes on positive real values. What I want to introduce in this video is how we can extend the exponential function into the complex numbers. So let's suppose that a complex number z equals x plus iy. Then the function e to the z, defined for complex numbers, can be written in the form e to the x plus iy. If we use the property of exponents for the sum of exponents and apply that with the case of base e, we can rewrite this as e to the x times e to the iy. Euler's formula states that e to the I theta equals cosine theta plus I sine of theta, so we can expand the e to the iy term as cosine of y plus I sine of y. So this entire expression becomes e to the x times parentheses cosine y plus I sine of y. If we really wanted to rewrite this in a plus bi form, we can write this expression in the form e to the x cosine y plus e to the x sine y times I. But e to the x times parentheses cosine y plus I sine y is the most common form for the exponential function in the complex numbers. If we look at the expression for e to the x, e to the iy, we can see that it's already in exponential form. If we let e to the x, e to the iy equal re to the I theta, which is the exponential form of a complex number, then r equals e to the x. In the exponential form, theta represents the argument of the complex number, or the angle between the positive real axis and the line segment going from the origin to the point on the complex plane, representing the complex number in the counterclockwise direction. Therefore, the two angles in the complex numbers, e to the x, e to the iy, and re to the I theta, must be the same for the two expressions to be equal. So theta equals y plus 2 pi k for all integer values of k. This is because a difference of any integer multiple of 2 pi in radians doesn't change the angle on the complex plane, since 2 pi represents a full circle in radians. So this means the absolute value of e to the z is e to the x, given that z equals x plus iy, and the argument is y plus 2 pi k for all integer values of k. Arg of z, which is the function representing the argument of a complex number, is a multi-valued function and can take on infinitely many values because there are infinitely many ways to represent any given angle between the line from the origin to the point and the positive x-axis. Another way to think about the absolute value is looking at the expression e to the x times parentheses cosine y plus I sine of y. Cosine y plus I sine of y always has an absolute value of 1, no matter what the value of y is. So the absolute value of the entire expression e to the x times parentheses cosine y plus I sine of y is simply e to the x, since any number multiplied by 1 is just equal to itself. The absolute value of e to the z being equal to e to the x means that the exponential function being defined in the complex numbers can still never equal 0, because e to the x is never equal to 0 whenever x is real. And the only way for a complex number to equal 0 is if the absolute value is 0. So I would like to show some examples of evaluating exponential functions with complex values. So let's say we have e to the 4 plus 3i. We can simply evaluate this using the formula for the exponential function. If we apply the formula, then e to the 4 plus 3i equals e to the 4 times parentheses cosine 3 plus I sine of 3. If we expand the expression, this equals e to the 4 times cosine of 3 plus e to the 4 times sine of 3 times I. If we put in the exponential and trigonometric values into a calculator, keeping in mind that we're working with radians here, we'll find that this expression is approximately negative 54.0522 plus 7.7038i. So here's another example. Let's say we have e to the I. In this case, if we assume that z equals x plus iy, then x equals 0, since this is a purely imaginary number, so the real part is 0, and the imaginary part, y, is equal to 1. If we use the formula, this just equals e to the 0 times cosine of 1 plus I sine of 1. If we expand the expression, this is equal to e to the 0 times cosine of 1 plus e to the 0 times sine of 1 times I. If we put in the exponential and trigonometric values into a calculator, we'll find that this expression is approximately this value. So let's say we have e to the 2, which is just the exponential function with a real number. If we plug this into the formula for the exponential function with complex numbers, we would still get the same value as we would if we just evaluated the function as a real-valued function. The real number 2 is still a complex number, and if we assume the form x plus iy, then the real part x equals 2, and the imaginary part y equals 0. A real number is just a complex number where the imaginary part is 0. If we apply the formula, then e to the 2 equals e to the 2 times parentheses cosine of 0 plus I sine of 0. This equals e to the 2 times 1 plus 0, which equals e to the 2 times 1, since cosine of 0 equals 1, and sine of 0 equals 0. Whenever the imaginary part is 0, which means z is a real number and y equals 0, cosine of y plus I sine of y equals 1, so the entire formula is just reduced to e to the x. This is why the formula is consistent with the real definition of e to the x. So this simplifies to e to the 2, which means we can confirm that the formula still works with real numbers.